Welcome to the Explainer. In this one, we're taking a super complex topic and breaking it down so it's crystal clear. All right, let's just jump right in. Today, we're going to unpack a really radical new way to think about building storage systems. We'll follow this roadmap right here, and it's all based on a spec that basically throws out some of the biggest rules we thought we had to follow in network design. Okay, first up. To really get this, we have to start with a huge fundamental question. This question really shapes our entire digital world. And frankly, most systems answer it by just creating powerful central authorities. So here's the big puzzle the DSM spec is trying to solve. How on earth can a global network of computers all agree on what's true without any clocks, without any leaders, without any digital signatures? How do you maintain one consistent history without someone in charge saying, yep, that happened? The answer? Well, it's a complete flip in how we think about this stuff. And here's the core philosophy. Maximum determinism, minimum trust. The whole idea is to build a system that runs on pure, verifiable math. You don't have to trust some powerful company or group in the middle. The goal, and the spec says this directly, is to crank up the determinism all the way and dial the need for trust way, way down. So what does that actually mean to be deterministic? Let's take a look at how that philosophy completely changes the design of a network. Okay, this is where it gets really interesting. Look at the difference here. On one side, you have your typical networks. They got special players, right? Validators, leaders, sequencers, people who are trusted to say what's what. They need clocks to keep everything in sync. The DSM way, it just gets rid of all of that. No leaders, no timestamps. And get this, the nodes that actually store the data, they never, and I mean never, sign anything. So think of it like this. It's like a cosmic recipe. Imagine everyone has the exact same recipe book, and all the ingredients are laid out in public for everyone to see, right? The data, the signals from the nodes, who's participating, it's all public. The recipe itself is just a set of pure mathematical rules. So anyone, you, me, anyone on the planet can follow that same recipe with those same ingredients, and we will all bake the exact same cake. You don't have to trust that my cake is right. You can just bake it yourself and prove it. Okay, that brings up a pretty big question, right? How is any of this secure? If the nodes that hold my data aren't even signing for it, how do I know it's safe? How do I know it hasn't been messed with? This is absolutely crucial to understanding how it works. The nodes are designed to be perfect librarians, and the spec even calls them dumb storage nodes, which sounds funny, but it's on purpose. See, these librarians, they don't read your books. They don't care what's inside them. Their only job is to follow a set of unbreakable mathematical rules for where the data goes and exactly how much space it takes up. They just store and mirror bytes. That's it. That's their whole job. So how do they track all this data? They use this really clever data structure called a sparse Merkle tree, or SMT. You can just think of it as a way to create a digital fingerprint for the entire library of data. It takes everything a node is storing and boils it down to one single unique code. And the cool part is, if even one tiny little byte of data changes anywhere, the entire fingerprint changes completely. It's super sensitive. And this is how that verifiable history gets built, piece by piece. At the end of every cycle, a node publishes something called a byte commit. Now, this little package is super important. It has the new fingerprint for all the current data, but here's the kicker. It also includes the fingerprint from the previous cycle. So you get this unbreakable cryptographic chain. Each new state points directly back to the one before it, creating a perfect, verifiable timeline, all without a single clock. Okay, so the data is secure, but what about the network itself? How does it grow or shrink? Usually you'd need a vote or some committee would have to decide, but with DSM, you guessed it, it's just more math. It all boils down to these public signals that every node sends out. It's pretty simple, actually. If a node starts getting too full, say 85% or more, it just raises its hand and sends out an up signal. If it's getting too empty, like 35% or less, it sends a down signal. And these signals are totally public. Anyone can see them. So then, the network protocol just looks at all these signals and does a simple count. How many up signals are there? How many down? And that tally gives you a number, the position delta, or delta P. Now, this isn't some vague suggestion. It's a deterministic calculation of the exact number of new spots the network needs to add or remove in the very next cycle. And this is the really wild part. Even choosing who gets those new spots is totally deterministic. The system just takes a bunch of public data, mashes it together to create a unique salt for that cycle. Then, every single application to join the network is put through a mathematical function with that salt. Whoever's application produces the lowest number wins. That's it. No leaders picking their friends, no expensive auctions, no random lottery. It's a pure mathematical contest that everyone can verify for themselves. So, when you build a foundation like this, one that's based on pure verifiable math instead of trust, what can you actually build on top of it? This is where things start to get really mind-bending. Let's pull a really powerful example straight from the spec itself. It's called a deterministic limbo vault, or DLV. Yeah, the name sounds a little out there, but the idea behind it is an absolute game changer. Okay, imagine you want to lock something away, like a digital time capsule that can only be opened under certain conditions. Here's how it works. First, you publish what's called a pre-commit. Think of this like showing everyone a locked box. You're making a public commitment to a secret, but you're not revealing the secret itself. The network just holds the box. It has no idea how to open it. Then, later, you publish the reveal material. That's the key. The network doesn't use the key to open the box. It just uses math to prove that your key is, in fact, the one and only key that fits the lock you published earlier. It verifies the proof without ever needing to hold the secret.
And that same basic principle makes something else possible: content-addressed token policies. Just think of it like this. It's a rulebook for a digital asset that can never be changed. And here's why. The address of the rulebook on the network is the cryptographic fingerprint of the rules themselves. So if you tried to change even one comma in the rulebook, the fingerprint would change, and therefore the address would change. The rules and the asset's identity are fused together forever.
When you step back, the big idea here is a massive shift in who holds the power. In most systems, you have to trust the operators. You have to hope they're being honest. In this model, you don't. The system is designed from the ground up to be so transparent, so mathematically provable, that it actually hands you the tools to verify everything for yourself. Verification stops being a job for a powerful few, and it becomes a right for every single person who uses the network. And that really leaves us with one last big question to chew on. If we can actually build a system that creates perfect verifiable memory, a system that can agree on what's true based on nothing but math, with no rulers or central authorities needed, what does that unlock? What will we build with it?